Okay, thanks for your introduction. Hello, everyone. I am glad to be here to share our recent work with you. Today, I'm going to talk about TFT-based piezoelectret sensor and its application in arterial pulse measurement. Today's presentation will be four parts. The first is background. While the cardiovascular diseases deeply impact a person's life, and the variable pulse measurement is a valuable tool for enhancing the management of cardiovascular system because the pulse waves contain a wealth of physiological information such as heart rate, blood pressure, and arterial stiffness. And the wearable pulse measurement can support continuous and non-invasive monitoring and provide some personal health management and remote monitoring. And it can works based on various detection principles such as optical, mechanical, and image. Today, we are going to talk about mechanical sensors. This method can directly detect pressure change on the skin caused by the arterial pressure, providing trace and real-time pulse wave information. And among mechanical sensors, piezoelectric sensors stand out as a type of active pressures sensors. Yes, they work based on the electrostatic induction principle, and they exhibit obvious advantages such as high signal to noise ratio, sensitivity, rapid response time, easy fabrication, and cost efficiency. However, there is a big challenge faced by them, that is their high output impedance because they are capacitive in nature. Well, this can easily make an impedance mismatch with some conventional readout circuits, further resulting in some signal distortion. In our work, we think integration with thin film transistors, that is TFTs, might be a promising solution. While TFTs have high input impedance, making them suited for impedance conversion in some capacitive devices. In addition, TFTs can be fabricated on a flexible substrate through some microfabrication process, making them suitable for some skin-based measurement. Yes, to verify the feasibility of the proposed method, we firstly design the device structure and do some basic simulation. This is the sketch of the designed sensor. Is mainly consisting of two components, the TFT and the piezoelectric device. And the gate electrode of the TFT is connected to the bottom electrode of the piezoelectric device. And its effective sensing area is small compared to some conventional piezoelectric sensor. And the red picture is the working principle of the device. When a pressure is applied to the device, the capacitance between the upper and the bottom electrode will change, further resulting in some charge redistribution between the gate electrode and the bottom electrode. And then a gate voltage can be generated and acting on the semiconductor layer. Oh, sorry. This is a simplified model, and by numerical simulation, the relationship between the gate voltage or potential and the displacement of the upper electrode can be explored. As shown in the red picture, it can be seen that under Klein stimulus, the peak-to-peak gate voltage is unaffected by frequency and dependent on the displacement. And we also do some advanced simulation using pulse waveforms. Well, compared to the sensor without TFT, the piezoelectret sensor with TFT can more accurately reflect pulse waveforms. After verifying the effectiveness of the proposed solution, let's move on the experimental. The left picture is the detailed microfabrication process, and mainly including the fabrication of the TFT, the macrostructured EcoFlex spacer, and electrode charging and assembly. In our fabrication, the macrostructured EcoFlex spacer is fabricated by spin coating EcoFlex on the PET template made by some hot pressing. In our test, the TFT is the IG0 TFT is chosen in our test because it's a stable operational performance and low cost. Yes, and the sensing performance of the TFT-based piezoelectric sensors is tested. We firstly explored its frequency-dependent output characteristics. We compare the output current of the sensors with and without TFT under the force with different frequency, while the sensor compared to the sensor without TFT, the piezoelectric sensor with TFT is scarcely influenced by frequency. This undoubtedly enhance the sensing accuracy. And then we explore its static force response. The left picture is the comparison of output current of two devices under stepped force. The device without TFT can only generate peak current when the force change with no signals under static force. And the sensor with TFTs can exhibit staircase waveforms with the pressure increasing from the 1.8 kPa to 4.1 kPa. And can maintain unchanged under static force. Overall, with the assistance of TFT, the piezoelectric sensor can mirror static force. And we also test its sensitivity. As shown in the right picture, it exhibits high sensitivity in higher pressure range. This phenomenon is different from some conventional pressure sensor with some softer materials. This result is mainly contributed to the amplification characteristics of TFT. Yes, after collaborating the piezoelectric sensor with TFT, we tested its ability to measure arterial pulse signals. In our test, a healthy volunteer in her late 20s put her right wrist on the device, and the external pressure and the arterial pulse waves can be recorded simultaneously. And the right picture is the enlarged view of the pulse waves, exhibiting the device's ability to capture the subtle waves. And according to the waveforms, various clinical information regarding the cardiovascular system can also be obtained, such as the radial artery augmentation index and time difference. In our test, some calculated results are compatible with scientific dates online. And in our further study, by fabricating some TFT arrays through fabrication, our designed sensor can be easily updated to some array configuration to achieve special temporal pulse measurement. Just like the map can be obtained in our test, and this map can illustrate the amplitude difference depending on the position. Like that, the maximum amplitude can be obtained in the Pixel 2. It means that the Pixel 2 is located on or nearest to the radial artery, and it can exhibit the most accurate waveforms. Yes, and finally, it's a conclusion. The TFT-based piezoelectret sensor can measure static pressures. This is important for the pulse measurement, especially for the DC components. And with the assistance of TFTs, the piezoelectret sensor exhibits a good sensitivity over a wide pressure range. And the output of the sensor can reflect the pulse wave features, providing clinical information. And the TFT-based sensor can be explored to the array formation to achieve special temporal pulse measurement. And thanks all the team members for their support for this work. And we are grateful for all the funding support. Thank you for your listening.